Yeah. Thank you. Thank you for having me. So my talk will be about first results that have been obtained during this collaboration of the two departments at Tbilisi State University. So on one part, it was logicians and from the disciplinary department, and from the other side, there were immunologists. And I will mainly speak about logical and algebraic part. Okay, then I'll use this one. Is it on? Okay? Is it better? Okay, so I will mainly speak about, of course, the mathematical part, but I will also give some sketch of how we are trying to use these results in biology. So what are the global objectives? So the main objective is to give a logical based system, which will give us some tools and some mathematical techniques to analyze some properties and states of a biological system. And in hindsight, we want to give immunologists, in this case, some useful tools for diagnosis and maybe some, in best case scenarios, tackle some diseases as well. So the study of biology is not new. So it was first proposed in 1930s when Woodger proposed discussing biology by means of the precise mathematical reasoning. And then in the 50s, Rashevsky and Rosen developed the relational theory of biological systems. So what we're trying to do is to give a logical system and in particular relational systems, which will have the applications in immune systems. And what we're concentrated mostly is the special subkind of cells, which are T cells, and they're special in the sense that they possess a sort of knowledge. They have a sort of knowledge of their own states and also the states of other cells, and their communication between the cells is dependent on this knowledge. In our case, we will introduce the box and diamond, and the box box alpha means the agent knows proposition alpha, and what we propose will be the quasi-knowledge, the notion of quasi-knowledge, and I will speak about it later, so what it will mean, and also we will have the appropriate diamond Q as well, which will be dual of the box Q. I assume some knowledge of MV algebras because the main tools I will be discussing are based on Lukasiewicz logic and their appropriate algebraic systems, which are MV algebras. And basically, it's the most, probably most famous generalizations of a two-valued Boolean algebras, and here we have the truth values of on 0-1 interval, and here the algebra L is the main MV algebra as it generates the whole variety of MV algebras. And but what we concentrate mostly is will be the MV algebras that are not semi-simple. So the semi-simple means just that it has a non-zero radical. So the intersection of all of its maximal ideals is not zero. And exactly these elements that are contained in the radicals are called infinitesimals. And these infinitesimals are such elements that no matter how many times we can add it to each other, so we cannot get zero. and the first example of such non-simple MV algebra was given by Chang, and it's it was C algebra defined by him. So the algebra is actually given here. So it is a chain where we have practically we have a set of natural numbers with their natural ordering, and on top of that we have again one copy of a set of natural numbers, but with the reversed ordering. And the MV operations are defined in quite a simple manner, that we just take the summation of the naturals, and if we have co-elements, then and the negation is will be just one minus NC. So why do we take and why do we use this algebra instead of MV? Because it has some special properties that sets it apart. And the main fact is that the algebra C is the simplest MV algebra that contains infinitesimals. And in fact, all of its elements are infinitesimals. So the first part, after 0, they are all infinitesimals, and on the second part are co-infinitesimals. And also, if we take any semi-simple MV algebra, it will contain the copy of the C as a subalgebra. And it is generated by its radical, and if we take the factor algebra by its radical, we'll get 2-element Boolean algebras. So up to infinitesimals, it's like Boolean algebra 0, 1. So in a sense, for our purposes, it somewhat acts like a 4-element algebra, so where we have 0 and 1. And besides them, we have the elements that are quasi-0 and quasi-1. And this gives us tools to somehow model this value of quasi-truthness and quasi-falseness. It is generated by an atom, and this atom will interpret as a quasi-false truth value, and its negation will be quasi-true. And if x is quasi-true, then x in the power n is quasi-true as well. And by contrast, if we take an MV algebra L, which was given earlier, and which is we are generating the variety of MV algebras, there is no truth value that will have that will satisfy these statements. And if so. These algebras, these MV algebras that are generated by the infinitesimals are called perfect, and they form a subcategory of MV. It is not a subvariety, as even if we take like C squared, it will not be perfect anymore. So, but we can take a radical and generate the algebra from it, and then we will have perfect copies, perfect subalgebra of it. And we will use the definition of MVC and as the variety generated by an algebra C, and the class of perfect MV algebras, of course, will be included in the variety MVC. Here I will give some also notion of monadic MV algebra that was given and studied by Routledge, and that later was characterized by Grigola, Dinole, and others by means of the pairs of the algebra, MV algebra, and its subalgebra. And we will add one more axiom, which is this one. And this axiom actually defines the subvariety of MVC from the variety of MV algebras. So this is axiom that gives us the perfect MV algebras from all the others or other ones. So we construct appropriate logical system. Of course, we start from the Lukasiewicz axioms, and then the corresponding axioms for the box Q, and also give what we don't give explicitly the axioms for diamond, but diamond is of course given defined by the box, and plus we need an extra axiom to catch these infinitesimals as well. So in the end, we will define the logic ELPC, which we use for this for our purposes. And what we get is that the MMVC algebras are the algebraic counterparts of ELPC. So the formula phi of this logic is a theorem, if and only if it is valid in all MMVC algebras. I will, one of my questions that I was going to ask was answered about an hour ago, so I already know you quite well. You quite well know Kripke frames, so I will skip this slide. So the difference is in the evaluation part, so where we get evaluation, we evaluate these formulas and propositional variables in the algebra C. So the evaluation is done on the algebra, on Chang's algebra C. And additionally, if we have if the evaluation on some state, if on some states the evaluation is in the negation of the radical, then all of its successors should be evaluated in this negation of the radical as well. For box Q, we have the join, and for diamond Q, we have join, and for box Q, we have meet of on all these evaluations of on all the successors. We also give the notion of quasi-validity. Of course, we say that its formula is modal valid if it's evaluated in all finite Kripke models, and we'll say that it's quasi-valid. It's if it's evaluated to the negation of the radical in all Kripke models, and in the same manner we can define the modal one-satisfiability and modal quasi-satisfiability as well. And we can show that that any formula phi of this logic is modally valid, and vice versa. So now, so how do we want to use this as some tools to argue and speak about real biological systems? So we are concentrated on some, as I said, on special type of cells, which are T cells, like helper cells. But even those tiny minor parts have lots of variations, and here is given just small part of it. And each cell can have its state, so it can be activated. It can be activated by an input signal from other cell, and moreover, it can be aware of the state of other cells or itself. Well, at first, when we started and asked our collaborators to give some simple diagram of this communication, they came up with this simplest form of diagram. Of course, then we asked for a little bit more appropriate for starting point. And so what we trying to do is to give and to think about this system as a relational model. So we take these so these these cells, we think about these cells as the elements of the world, as the worlds, and the relation between them, about which in a real world case, in a real world scenario, is given by the and conducted by some lipids or other forms of communication between the live cells. We think about this as the relations between these elements and these worlds. And here is given some real world example as well. So in hindsight, we think we want to represent the immune system as a set of T cells with some actions between them. So the T cell will be an agent, and an action between those are the relations between those agents. And by using this analogy or representation, we can represent this immune system as a C-valued descriptive Kripke frame. We give the notion of activation and quasi-activation, which somehow translates the validity and quasi-validity of the formulas. So they're defined in a straightforward manner. We will say that the cell is activated if its evaluation is 1, it's not activated if evaluation is 0, it's quasi-evaluated if it's evaluated to the negation of the radical, and not quasi-activated if it's evaluated to the radical of C. And the one type of function that if the function from this set of the possible words to C is, we call this function an epistemic state function if it preserves that if the following statements are true. So if something evaluated to 1, some state, then all the successors should be evaluated in 1 as well. And the same holds true if it have evaluation to the negation of the radical, all of its successors should be evaluated to the radical as well. If we take an evaluation and define a function, if we take an evaluation E and a function phi, and we can define the formula S E phi from W to C, so that S E phi W is E W phi. So, and we say that this formula is labeled by the evaluation E if this S E phi is an epistemic function and denoted by the ESE. And then we construct the transformation. So we're trying to model the transformation process from one epistemic state to another. And we call it the phi activation of the elements on the points of W. This is a way to represent how epistemic information changes dynamically. This can be, this may be due to some changes of internal system, or it may be also be some new epistemic information based on experiments, and which will produce some new information about the points of W. And And to know facts about this function means to know the facts about the possible variations of this epistemic state of the system. And the main problem will be then to somehow represent those variations and describe those variations by the formulas. And of course, the real life values of these functions has to be defined, and they are dependent on the types of cells that we will be discussing and that we will be modeling, and it's some experimental data is needed, and we have some plans already for that. But our part, of course, is to do the mathematical to give the mathematical tools to describe those states. And also we have to note that it could be of interest to explore the possibility to check whether a given collection of epistemic states we can find a formula that represents such a state. So this is another direction, if you say so, for the analysis. And this was the main part. Thank you.